Hello and welcome back to this fifth lecture on Introduction to Finite Field for Error Control Coding. My name is Sumit Kumar Chaube and today we are actually going to discuss extension field or extension of GF2, basically GF2 to the power M. Okay, so let's start. Okay, so let's begin our construction of Galois field GF2 to the power M. To discuss it, we generally, to actually construct a Galois field of GF2 to the power M, we are going to use a primitive polynomial of degree M. As discussed in the last lecture, a primitive polynomial is basically an irreducible polynomial of degree M, but its order is 2 to the power M minus 1. So the roots of primitive polynomial are not found in GF2, rather than they are found in GF2 to the power M. So we are going to use this roots of primitive polynomial to actually construct a extension field GF2 to the power M. So initially we are going to start with two elements 0 and 1 from GF2, and we are going to introduce a new symbol or new element alpha, and we will define a multiplication as follows: that 0 times 0 is basically equal to 0, 0 times 1 and 1 times 0 is actually equal to 0, and 1 times 1 is 1, where 0 is the 0 element and 1 is unit element. And this 0 times new element alpha and alpha times 0 is actually equal to 0. In the similar manner, 1 times alpha and alpha times 1 is actually equal to alpha. So in this manner, we are also going to define alpha square, alpha cube, and alpha square is simply alpha times alpha. Alpha cube is simply equal to alpha times alpha all the way up to j times. So we will we can have alpha cube in this manner, and alpha j will be equal to alpha all the way j times. Okay, so this is how we are going to define multiplication over 0, 1 and alpha, and then we will have element alpha square, alpha cube, alpha j. Okay, so now we have a set which is f, and it is basically 0, 1, alpha square, alpha cube, alpha j, and it's going to continue for some time. Now let's define a primitive polynomial px of degree m over GF2. So we can always get a polynomial of degree m over GF2, and we are going to assume that alpha is actually root of this primitive polynomial. What that means is that p of alpha is equal to 0. Since px is actually a factor of x to the power 2 to the power m minus 1 plus 1, right? So alpha, if we put equation alpha in this, it is going to be equal to 0. So alpha into 2 to alpha to the power 2 to the power m minus 1 plus 1 becomes actually equal to 0. So we will have alpha 2 to the power m minus 1 equal to 1, and you can understand that this is the only value that is becoming 1. In this manner, alpha to the power I is never going to be equal to is never going to be equal to 1. Okay, for all I less than 2 to the power m minus 1. So now we have a set, and this set is finite, and it is going to contain 2 to the power m element. Okay, so we have 0, 1 and all the way alpha 2 to the power m minus 2, because alpha 2 to the power m minus 1 is actually equal to 1 only. So 1 is generally written as alpha to the power 0, or it can also be written as alpha 2 to the power m minus 1. Okay, so you can see that this is going to be a commutative group under multiplication. If we multiply any two of these elements, we will get an element in the field, and it's also going to be commutative. So this is going to be a commutative group. Non-zero element of this set fx is going to be a commutative group under multiplication, and that's very easy to see. Okay, now we are going to define addition on this set F such that F forms a commutative group under addition. To do that, let's simply write for I equal to I less than I greater than equal to 0 and less than 2 to the power m, we can always have xi equal to qix px plus aix, where a, when we divide xi by px, our primitive polynomial, we will have a something like this, okay, where aix is remainder. Okay, so aix is generally a polynomial of degree m minus 1 or less. So aix is a remainder polynomial and its degree is m minus 1 or less. So we have a polynomial of degree m minus 1 or less when we divide this xi for I is equal to 0 to 2m minus 1, we will have a aix. Okay, so here aij, the coefficient of this polynomial, are element of GF2, means they are either 0 or 1. Okay, since xi and px are relatively prime, we have aix never equal to 0. So since this is the definition of primitive polynomial, that it doesn't divide any polynomial except x to the power m plus 1. So in that sense, it is this polynomial and this polynomial is always going to be relatively prime. So we will always have this remainder polynomial aix. Okay, now here we have a theorem that for 0 less than equal to I not equal to j, less than 2 to the power m minus 1, aix is not equal to ajx. So if you take xi and xj, where ij both are between 0 and 2m minus 1, then if you divide it by this primitive polynomial, the remainder is always going to be different. Okay, so that's very easy to prove. Suppose that aix is actually equal to ajx, then xi plus xj will be written like this, right? But since aix is equal to ajx, this summation using XOR is going to be 0. So this will become 0 and you have xi plus xj equal to qix plus qjx times px, which is again a violation of the fact that qx, that px is not divisible, is not going to divide any other polynomial except x to the power 2 to the power m minus 1. Okay, so that's wrong. It means that these two remainder aix and ajx must be different. So we have 2 to the power m minus 1 distinct non-zero polynomials of aix of degree m minus 1 or less. So replacing x by alpha, we will have alpha to the power I equal to aix, because again p of alpha is actually equal to 0. So this part here will become 0. This part will become 0. So you have alpha I is equal to aix and that is equal to this polynomial. Okay, so the 2 to the power m minus 1 non-zero element 1 alpha square alpha 2 to the power m minus 2 in F can be represented by 2 to the power m minus 1 distinct non-zero polynomial of alpha over GF2 with degree m minus 1 or less. Okay, the 0 in F can be represented by a 0 polynomial. So we are going to define an addition as follows, that 0 plus 0 is equal to 0 for all I between 0 and 2 to the power m minus 1, 0 plus alpha I is actually equal to alpha I, and for any other value, if you for all I and j between 0 and 2 to the power m minus 1, alpha I plus alpha j is actually equal to addition of the polynomial representation of those elements, and that is actually written here. So it is easy to see that F is a commutative group under addition, and polynomial multiplication satisfy distribution law. Since a polynomial multiplication always satisfy distribution law, and this is going to be a commutative group under addition, because if you add any of these of two, you will always going to end up with another polynomial that is in the group. Okay, so we can say that F is a finite field of 2 to the power m element if we define our addition and multiplication in this way. Okay, so now we are going to actually construct a field, and for this we are going to construct GF2 to the power 3 using x cube plus x plus 1, and this is the primitive polynomial that we are talking about. So directly from here we have two relations, that alpha cube plus alpha plus 1 is actually equal to 0. It means that alpha cube is equal to alpha plus 1. Okay, and the multiplication, and another is that this is always going to be a factor of x to the power 2 to the power 3 minus 1, means 7 plus 1. So from here we will have alpha to the power 7 is equal to 1, right? So here 1, this 0, now we have two form, one is power form, another is polynomial form. Now power form will be used for multiplication, and we will use the fact that alpha to the power 7 is equal to 1, so it is going to repeat after that. So alpha to the power 8 is going to be alpha, so this is going to be a cyclic group under multiplication. Okay, in the similar manner, now we have polynomial form. This is going to be used for addition. So power form is going to be used for multiplication, and polynomial field is going to be used for addition. So here you can say that 0 will be 0 in both polynomial and power form. 1 will be 1 in power form, and in polynomial form it can be written as alpha to the power 0 or alpha to the power 7. Here it can also be written as alpha to the power 7 or alpha to the power 0, but we generally denote it by 1 only. And alpha is going to be alpha both in polynomial as well as in power form. Alpha square is again going to be alpha square. Now alpha cube will be equal to alpha plus 1, right? Here you can see that alpha cube plus alpha plus 1 is equal to 0. So alpha cube is equal to alpha plus 1. So we have alpha plus 1 here. Alpha to the power 4 will be simply alpha cube times alpha, and that is going to be alpha square plus alpha. Now alpha to the power 5, alpha to the power 5 is actually going to be alpha to the power 4 times alpha, and alpha to the power 4 is actually alpha square plus alpha. So we are going to multiply this with alpha, and we will be having alpha cube plus alpha square, and alpha cube is actually equal to alpha plus 1. So we have alpha square plus alpha plus 1 alpha to the power 5. So this will be equal to alpha square plus alpha plus 1. Okay, and now alpha to the power 6 will be this time alpha, so this will be equal to alpha cube plus alpha square plus alpha, and then it will become alpha square plus alpha plus 1. So alpha this is going to be 0, so we have alpha square plus 1. So alpha to the power 6 will be equal to alpha square plus 1. Now this is the polynomial form that we are going to use for addition, and this is the power form that we are going to use for multiplication. And you can actually construct a Cayley table here. So your job, your homework is to construct the Cayley table for GF2 to the power m. Okay, now next we are going to see another finite extension field GF2 to the power m, and this is we are going to generate using the primitive polynomial x to the power 4 plus x plus 1. So from here we actually have alpha to the power 4 is equal to alpha plus 1, and alpha to the power 15 is going to be equal to 1. Okay, so I have actually written some of the power form and polynomial form. Actually power form is very easy to write. It's always going to be 0 1 and then alpha and all the power of alpha all the way to the power 2 to the power m minus 2. So 16 minus 2 here in this case, so you have 14. So this is going to be our power form, Now we have to write polynomial form. I have written polynomial form of certain element. You have to write, now let me do just one, alpha to the power 7. So alpha to the power 7 will be actually equal to alpha to the power 6 times alpha, right? And alpha to the power 6 is written as alpha cube plus alpha square. So alpha cube plus alpha square times alpha, and this will become alpha to the power 4 plus alpha cube. But alpha 4 is actually equal to alpha plus 1. So we have alpha cube plus alpha plus 1. So this will become alpha cube plus alpha plus 1. And you have to find out rest of these. So this is again going to be homework for you, that calculate the polynomial form and then represent it in Cayley table. Okay. So thank you for tuning in.